Welcome to AP Calculus Review, Part 4. I'll first be going over differential equations. One way you can solve a differential equation is by using separation of variables. First, what a differential equation is it comes in the form of dy over dx equals something, right? It gives you your dy dx, and most of the time when you have differential equations, you may be able to solve them for y. One way to solve them is using separation of variables, and I'll give a couple examples. We have dy over dx equals x over y. Now how do we solve for what y is? We can use, so you can put all the dy's on, you put all the y's on the left side and all the x's on the right side. So I'd multiply this by y and multiply by dx to get y dy that equals x dx, right? Now what we can do here is you can integrate both sides. So for this one, we'll use the reverse power rule to get y squared over 2 plus c equals x squared plus 2 x squared over 2 plus c. These are just combined into one big plus c on the right. So, and the reason why the c's don't cancel out is because we're doing two entirely different integrations, one here with respect to y and one here with respect to x. So we're still going to need a plus c on the end here. And what this is right now, this is a general solution. So this could work for any value of c. First of all, we could solve this out more if you want to. Multiply everything by 2 and square root right, and this would give us our y, which is plus or minus the square root of x squared plus c. So that's our general solution. Now I'll go over a particular solution where we get a real straight equation. So I'll do dy over dx equals y cosine x, right? And we have it's called the initial condition. That when x is 0, y is equal to 2. So what we do is we use this initial condition, and we're solving out our differential equation to actually get a value for c. So first I'll use separation of variables by moving things over. So first I'll divide by y, get dy over y, multiply by x to have cosine x dx, and now we'll integrate both sides. So for this one we get ln, the absolute value of y, equals, antiderivative of cosine x is sine x plus c. So what we could do is we could just use this to find c right here by plugging in our value for y and our value for x. So ln, the absolute value of 2, which ends up just being 2, equals sine 0 plus c. And the sine of 0 is 0, so we just have c equals ln 2. Right, so now we keep working on the equation. ln of the absolute value of y equals sine x plus ln 2 absolute value of y equals to e to the sine x plus ln 2, which is the same as e to the sine x times e to the ln 2, or 2 e to the sine x. And the last thing we're going to do is to get rid of this absolute value, is y equals 2e to the sine x. And the reason I got rid of this absolute value and put a positive y here is because our initial condition is positive here. If we had a negative initial condition, like -2, right, then we just got an ln of the absolute value of -2, which ends up being ln 2 anyway. So if I had -2, this would be -y equals 2e to the sine x. So y would be equals -2e to the sine x. But since we have a positive initial condition here, then we're going to have a positive y that comes from our absolute value. It's the same situation for square roots. Like if you had to, like y squared equals like x squared something, right? Kind of like we had up here. This initial condition would help us determine whether our sign here would be a plus or a minus. Right. Next we'll go over how we can use differential equations to model exponential growth. So remember the formula for just a standard like exponential equation is going to be a times b to the x. Right? This is like your nice standard exponential function. This can also be modeled using a differential equation. We can use dy or dt, but these can really be anything. This could be w, this could be h, anything really. It's the same idea. Equals ky. If I were to solve this out, right now, yeah, I'll solve this out right now. So we have dy over y equals k dt. Remember, k is just like any constant. This could be 1, 2, 3, so on. Now, integrate both sides. Get ln absolute value of y is kt plus c. We're going to use e both sides to get rid of the ln. Now we can just use our exponential properties to get ce to the kt. Right. So y equals ce to the kt. This is standard form for if you're solving an exponential like differential equation. The c represents your like initial amount. This could be like population or an amount of money or something like that. E is just E. Remember, that's like your 2.7 1, so on. K helps determine like how fast it grows. And your T is your like independent variable. It's just like your X. Your T is your amount of time. You can mean seconds, minutes, years, whatever it gives you. So this is gonna be your what the solution looks like for an exponential differential equation. We also go over like doubling time. You can set up doubling time by using 2 equals e to the kt. Sometimes it'll most likely give you your actual doubling time, or this value for k right here, and it may like ask you to solve for the other. If it was like tripling, maybe 3 equals e to the kt. And the reason I'm leaving the c out is like, so remember c is just our initial population or initial amount. Double that would just be 2c, so the c's would just cancel out. So I just have 2 equals e to the kt for that doubling time. Slope fields are used to graphically model differential equations. Sometimes you may have like differential equations that you can't solve using separation of variables, like we were just doing. So it may help to use a slope field instead. This right here is a slope field, dy over dx equals 1. Every single slope right here is 1. No matter what your x or y value is, it's always just going to be 1. Alright. This is dy over dx equals x. So when your x is 0, you have a slope of 0. When your x is 1, you have a slope of 1. When it's negative 1, you have a slope of negative 1. So on. This is 2, 3, 4. Right? This only relies on your x value. There's no y in here. So notice like no matter where you are as your y, it like see here, it stays the same. This is dy over dx is equal to y. So when your y is 0, 0, 0. When it's 1, 2, 3, negative 1, 2, 3. And so this one doesn't rely on your like x. See, it's the same from left to right. Here's some slightly more complicated ones. Dr over dx equals x plus y. This takes both your x and y into account. So if you have, 0 plus 0, that's just 0. Here it's 1 plus 1, so that's the slope of 2. Here this is negative 1 plus 0, so this is a slope of negative 1. And the same for all of these. Notice you can't solve this using separation of variables like we were doing earlier. So it's helpful to use like a slope field to analyze what that function might look like. Yeah, another thing about slope fields is that if you sort of draw like a line, you can get a feel for what the function may look like using a slope field. For this one, we have dy over dx equals y times 1 minus y. This could be used for like logistic equations. Right over here, where your y is 1, you have a slope of 0, because this term would be 0. When y is 0, your slope would be 0. And then you just like solve it out for all of these. This is for y equals negative 1. So plugging that into here, we'd get a slope of like negative 2. Right? So on. That's the slope field. Now this one is negative x over y. Notice that this looks like it can make a circle. This is more like circular slope field. It's negative x over y. I'm going to move on to integral analysis and applications. Interpretations of integrals. So remember that your integral represents the accumulation of change, or the net change. And if you remember the fundamental theorem of calculus, this is most often used in many integral interpretation problems, where maybe you'll have like one of these, you'll have your integral and you just solve for this other value right here. So this equation is extremely important to memorize and use. Particle motion is another situation where you would need to use the fundamental theorem of calculus in many situations. One thing to note about particle motion right now is, so remember your position should be like s of t or x of t. The derivative of position is velocity, and the derivative of velocity is acceleration. Going back the other way, the antiderivative of acceleration is velocity, and the antiderivative of velocity is position. So you may also see particle motion problems that involve integration. One important distinction is the difference between displacement and total distance. Displacement is like the point where you start to the point where you end. It doesn't take into account anything that's like happened along the way. So if you have like this kind of velocity graph, you start at 0, you end at 0, so your displacement is 0. Right, so the displacement would be like the integral of just velocity. Total distance is the definite integral of the absolute value of velocity, or speed. Because this takes into account all of the little nuances that happen from on your way from point A to point B. So this graph would look something like this for speed, right? And so it take account all of the distance traveled, not just here where you have, if you travel like in the positive direction, and then you travel in the negative direction, and you end up back at 0. That's displacement. For total distance, you have how much you traveled in one direction, and then you have how much you traveled back, and it just adds those together. So that's why you take the absolute value, because your total distance will be positive. The area between two curves is represented by the formula the integral from a to b of f of x minus g of x. Right? If I have just two curves here, and I find the area between them, I'm going to take the area under the curve of the top one so the top one includes all of this area right here, minus the area of the bottom one. So leaving that bottom area out, we'll end up with our total area between these two curves. You could also use this for situations where you have functions defined in terms of y. I'll write f of y minus g of y dy. This could be useful if you want to do like your right function minus your left function instead of top minus bottom. So like if you think about like this could be like 4 minus x, right? And this could be square root of x. But since it would be easier to evaluate this by using like right minus left instead of top minus bottom, you could change these into terms of y. So 4 minus x, that would be so x equals 4 minus y, and then plug them into your area between two curves formula that way. Volume by cross sections. So now let's start going to how you can use integrals to calculate a volume. So sometimes the integral, which is like your area, when you're evaluating volume by cross sections, this could be like the base of a solid, right? And try to draw like a 3D representation here. So you have like your function here, like your area. Let's say the cross section was a square, so you'd have like a square here, and you keep going. So you slowly get like smaller and smaller. So you can sort of see how the solid would look. What you're doing is you're finding the volume, the exact volume of this solid here. Your cross sections may be perpendicular to like the x-axis or the y-axis. If it's perpendicular to the x-axis, you're going to be doing your calculations in terms of x. If it's perpendicular to the y-axis, you'll be doing it in terms of y. You want to change everything to terms of y, not just your function, but also your bounds. Right? So we have like the fundamental idea of what the cross section looks like. And I'll start writing down some formulas. So for squares, it's going to be the integral of your function squared, right? That makes sense, but square is squared. And because you're taking this for each like infinitely small slice, you're taking a square. So that's what that squared is doing. It's doing it over and over again. So I get the volume of all of these little squares combined, and then you get like your volume. For like a rectangle, you it could really be anything. It could give you like, what if I try to use the same example, same sort of shape? You just be like, oh, you have a rectangle with a height of 3, right? And so all these rectangles would have the same height of 3. So this would be like 3 times the integral of fx dx. Or another thing it could be you could say like your height is going to be twice your base. So what that means is you have 2 times your base, that's your height, and times your base again, which is your actual base. So this one would be 2 times your fx squared dx. For semicircles, it'd be pi over 8 times your function squared dx. Remember, these could also be dy if you're taking cross sections perpendicular to the y-axis instead of the x-axis. Alright. So the reason this is pi over 8 is because, I'll draw another diagram here. Semicircles, right? It's going to look something like that. I'll replace this f of x with b, right? Your radius is b over 2, because this is the diameter of your semicircle. So your radius is going to be b over 2. The area of that semicircle is going to be pi over 2 r squared. And your r is b over 2. It's pi over 2 because it's a semicircle. Alright, and so doing that, you get pi over 2 times b squared over 4, and pi over 8 b squared. And that's how we get this pi over 8 here. For semi-ellipses, it's kind of like rectangles. You need to be able to think of this kind of like how I did here. So the formula for the area of an ellipse, and I'll call these like R1 and R2. It's pi R1, R2, right? For a semi-ellipse, it's going to be half that, so pi over 2. That's your semi-ellipse equation for area. So your R1 is most likely going to be your like b over 2 here. So I call my R1, and then your R2 would be the height. So I'll write out pi over 2 height, whatever it gives you. It could be twice the base, or it could be a height of 3, or a height of 2, or anything like that, times fx over 2 squared, or I can more easily write that out as pi over 8 times h times f of x. And this could be squared, or it could not be squared, depending on, like, so if it's if you just have a set like height, like 3 or 2, then this would not be squared. Because remember, you need to think about this formula here when you're deciding how to make this semi-ellipse formula. So b over 2, or f of x over 2, is your R1. R2 is given in the problem. Alright, that's a much better way to think about it. Yeah, I'll leave it at that. You may also have cross sections of triangles. You could have an isosceles right triangle with the leg as the base. that's going to be 1/2 f of x squared dx. It's 1/2 because imagine just like taking a square, you cut it in half, and this is your isosceles right triangle here, and you have the leg as the base here. If you have it with a hypotenuse base, then it's 1/4 f x squared dx. Because now imagine you have the square, cut it into a fourth right here. This is an isosceles right triangle, and you have the hypotenuse as the base here. Finally, equilateral triangle. The formula for that is square root of 3/4 f x squared dx. This is a pain to solve it by hand, so it'd be much better to just memorize it. You can think of it like this. This is your equilateral triangle. Right, so these are all the cross sections. If you give like a square cross section, then you just do this simple squared, rectangles, semicircles. Semi-ellipses don't come up really often. It's the most complicated one out of all of these. You have isosceles right triangles with like the leg as a base or hypotenuse as a base, and the equilateral triangle. Now we're going to use the disk method to evaluate volume. And what we're doing here is we're taking a two-dimensional shape right here, and we're revolving it around the axis to make so this one, let's make like a, I don't know, just make like a sort of weird vase shape. Imagine that as like a vase, right? And we try to find the volume of this. You'd use the disk method for that. The key terms for these, it'd be like revolved around or about the, so this could be like x-axis or y-axis. Or this could also be any other line, like x equals 1, y equals 1, etc. I'm going to quickly write the formula. It's going to be the integral of pi times your function squared dx. So you can think of this as your like pi r squared, because this is your r when you're making this solid. It's called like a solid of revolution. So this would be your r, and that's why you're using just pi r squared, right? So this is for the x-axis. If it was for the y-axis, you'd do the same thing, but in terms of y. And I wrote C and D here instead of A and B because you're going to have to, these are also going to have to be in terms of y. Like this could be from 0 to 4, and this one maybe 0 to 2. You have to keep, remember to change those bounds. Right. So if it's y equals, if it's a line like that, then it's going to be a horizontal line. You're going to use x. X equals 1, that's going to be like a vertical line. You're going to use y. So if you have the x or y axis, then you can just straight up use these formulas here. But if you have a line that you're revolving around, I'll call it just C, right? Let's say I have this same thing, but I want to revolve it around this line instead, using the disk method. So now I have all this extra area. to call as my my part of this like solid. So this is minus c. Let's say this is y equals -1. So I'll just be adding 1 like this. It should just be minus -1, right? And that would make it like the area between two curves, kind of. Finally, we're going to use the washer method. The formula for that is pi f of x squared minus your g of x squared dx. This could also be in terms of y, depending on if you're like revolving around the x or the y axis. And it also works the same way if you're revolving around like any other line, not just the x or y axis. So this, let me just draw out. Something like that, right? And we're going to revolve it around the x-axis here. The difference between the disk and the washer method is that in the disk method, your area is touching your like revolution axis, but in the washer method, it's not touching it. So it's going to end up looking like a washer, right? Where it has an empty space in the middle. Your f of x would be your like top function here, and your g of x would be your bottom function. Now, if you had to use another line, not the x-axis, then I just put you put c here minus g of x minus c squared dx, right? And because we'd be taking the area between two curves, right? Where your second curve would be like your other line. Say you're revolving around like y equals -1 again, then it would be +1 here, +1 here, and that would give us the area of our washer, this formula right here. That's all for part 4, and that's also the last video of calculus AB. The next videos will be going over calculus BC content.